Okay, so before we get going in this video, I want to say that you've all thought about forces your whole life. I mean, you've heard the word force a lot, and it's something that you sort of have some idea of what a force might be. You know that when I push on the wall, I'm applying a force, and so you have some knowledge about forces. Work is not that way. Okay, work, you don't really have a preconceived idea of what work is, so it seems a little more vague to you. That's totally normal. I think over time, you keep at it, you'll start to get an intuitive sense for what work is. You really will. And work has a really important, it's really important because it relates to something known as energy. Okay, kinetic, potential energy, and so forth. Work has a deep connection to those things, which you have heard of before. So all I'm trying to say is that work is a really important idea, and if it seems a little vague to you, it's just because you probably never thought about it until just now, in the last video. Whereas stuff like energy and forces you've been thinking about. So we're on our way to talking about energy, but we have to get through work to get there. Work remains, however, a very important topic. And so what I want to do now is to extend our idea of work a little bit. Last time we saw that a work was any force acting through a distance. And I gave you the two different cases, the case where the force and the displacement were in the same direction and the case where the force and the displacement are not in the same direction. And I tried to say at the end that the second equation, FD cosine theta, was the fundamental one, and that the first equation, F equals FD, is a special case. So now I want to look a little bit more at work and how it operates. And I want to use a very simple situation. We're going to have a block. This could be my trusty eraser. I'm going to lift it from here to there. Okay? So let's say a few things about that very exciting demonstration I just pulled off. Let's say that, let's see my numbers here. Let's say the mass is 1.0 kilograms, which of course is much heavier than that particular eraser. But say the mass is 1 kilogram. Let's say that the normal force, that is the contact force between my hand and the box or the object, the eraser, that normal force is it 15 newtons? Is that the number I have? Yeah, 15 newtons. And let's say the displacement is the magnitude of the displacement, rather. Obviously, it's going to be up, so we would want to normally call it positive. But then the magnitude of the displacement is 1.0 meters. So I'm taking a 1 kilogram object and raising it 1 meter, applying a force of 15 newtons to it. Okay. As that object moves up and I apply this force to it, there are two forces acting on it. The normal force up and the weight down. Now what I want to do here is I want to calculate the work done by the normal force, and then I want to calculate the work done by the weight. Both forces act on the block, on the eraser, what have you. Both forces act on the eraser, and they both do work on it. Let's calculate and see how much work is done by each force separately. Okay? So let's find the work done by the normal force. Sometimes you'll see me write it that way. Work with a subscript. Okay? In this case, the subscript always indicates the force that's doing the work. Okay? So the normal force is doing the work. Okay? Well, we know in general that the work done by any force is FD cosine theta. Right? We're going to use this. This equation, if all goes well, is going to become very near and dear to your hearts and your minds, and you will close your eyes at night and you'll see it floating behind your eyelids. Okay? So we're going to use this equation to calculate the work done by the normal force and by the weight. So this is the work done by the normal force. That will equal, in this case, the force F is the normal force, right? That force there that you see in this definition is whatever force that you're interested in that's doing the work. So the work done by the normal force, we're going to put in the normal force there times d times cosine of what? What's the angle between the normal force and the displacement? 0. They're in the same direction. This is like the first case I showed you in the last video. The two are in the same direction, so it's cosine of 0 degrees. Normal force is up, displacement is up. No angle between them. It's 0 angle. But, as I also indicated to you in the last video, cosine of 0 is 1. So this comes out just to N times D. Normal force is 15 newtons. D is 1 meter. So we have done 15 joules of work through our normal force. Normal force has done 15 joules of work. Okay. Remember, this first force here is the force doing the work. Similarly, what is the work done by the gravitational force? The weight. I guess I could put W sub W. W sub G is more common. So work done by gravity. Well, it's going to be the weight, mg. That's our force. Right? In the first case, that was our force, the normal force. In this case, the force doing the work is the force doing the work is the weight, which is mg. So this is our force. So mg is the force, again, times the displacement. Right? It's Fd. F in the case of gravity is mg. So given a certain problem, you have to substitute in for F whatever the force is doing the work. In there, mg here. And then D, and then cosine of what? Notice, in this case, the displacement is up. Right? There's only one displacement. It's up here. We move the block from there to there. Displacement's up. But the weight, the force of gravity, mg, is down. What is the angle between up and down? What angle is that, right? You got one vector up, the other one down. What's the angle between those two vectors? The angle there. That's 180 degrees. So it's mgd cosine of 180. What is the cosine of 180? Plug it into your calculator and you'll discover, or maybe you already know. Who's to say? You'll discover that the cosine of 180 is -1. So the work done by gravity is m, which is 1.0 kilogram, times g, which is 9.81 meters per second squared, times d, which is 1.0 meters, times -1. So the work done by gravity is -9.8 joules. Yes, the work done by gravity is negative. Exclamation point. It's negative. What does it mean? Well, in one sense, it doesn't really mean anything. It doesn't have to do, number one, it doesn't have to do with direction. Okay, because this is positive work, this is negative work. It doesn't mean that this work is in the opposite direction of that work. any more than saying 15 degrees Fahrenheit is in the opposite direction of negative 9.8 degrees Fahrenheit. There's no direction to it. One of them is above zero, one of them is below zero, but there's no direction involved. So the minus sign here does not have to do with the direction of the work. There's nothing like that. Okay, there's no direction to work. It's a scalar. Okay, but there can be negative work, and whenever a force opposes the displacement, you get negative work. Okay, whenever the force opposes the displacement, or has any component that opposes the displacement, you get negative work. Okay, that's the deal. Okay, so gravity is negative work because gravity, the force of gravity down the weight, opposes the displacement. They're opposite each other in direction. One's positive y, one's negative y. 180 degrees. Now, given these two bits of work done, this is only one motion. So we had two forces acting as the block was raised, and so we have two different works done. One work done by normal force and another work done by the weight, by the gravitational force, by mg. Two, normal force and weight. We can also define the net work. Okay? Or I think the book might actually call it the total work, same thing. The net work in this case, work net or work total, I think is simply the sum of the works. So in this case, it's going to be the work of the normal force plus the work done by gravity. It's the sum of all the work done by all the forces acting. In this case, there's only two, and so we have two terms here. And so the net work done on the block as it's raised 1 meter is going to be 15 joules minus 9.8 joules, so that the work total is equal to what? 5.2 joules. That is the total work done, or the net work done by all forces acting on the block as it is raised up. Okay. Again, the negative sign comes because they're opposed, because the force of gravity opposes the displacement, which is up. Okay. And the net work is simply the sum. This is not a vector sum. You have to worry about triangles or components or sines or cosines or tangents or nothing. When you find the total work, all you do is you add up all the numbers. Unlike finding the net force, the sum of the forces. In that case, forces are vectors, so you have to worry about directions. Work is a scalar, so all you do is add up the numbers like back in middle school. You just add them up, or even elementary school. You just add them up. Don't worry about direction. There ain't no direction to it. So that's negative and net work. Next up, we're going to do another, I believe, example.